we're looking at finding the equation of a hyperbola given its graph. Now, one difference from finding the equation looking at an ellipse is that the hyperbola, we would have to kind of know where the center box is. Otherwise, you might not be able to figure out where your b square term would be. So you'll notice in these examples, anytime they're asking you to find equation of hyperbola and not giving you any other information, only looking at the graph, they're going to have center boxes drawn in for you. So it's good practice. So I'm going to look at part B and C with you, and then I'll let you try A on your own. So if we're going to look at part B first, as far as hyperbolas are concerned, I'd like you to kind of recognize the orientation of the hyperbola. You'll notice that it has a open upwards, open downwards sort of feel for it. So that kind of gives you a heads up that we have a vertical hyperbola. And when we look at vertical hyperbolas, the generic equation that goes with them, assuming, well, we're not centered about the origin in any way for any of these examples right here, so I'm going to use the HK version. When you're a vertical hyperbola, that's going to mean that your y squared term will come first. So we have y minus k squared over a squared minus x minus h squared over b squared equals 1. And so just a heads up to remind ourselves, you know, how are these different than the ellipses? Keep in mind that you do have a minus sign separating the square terms. And it does not matter in terms of who a square is, in terms of it being bigger or smaller. What determines whether you're a vertical hyperbola or a horizontal hyperbola is the positive term in your equation. So notice that the y minus k squared is the positive term, so automatically that means that the a square is right underneath it. The a square has no effect on the size of the a square has no effect. I have to repeat that. Just a little different than ellipses, so there's a big caution there. So with this vertical hyperbola, our job is to figure out who A and B are, and A kind of has to do with the vertices on the hyperbola. And so you can kind of see the way the box is drawn, we can see exactly where they're located. But with this center box being drawn, it doesn't hurt to draw the asymptotes through the diagonals. That might center you in on the center. No pun intended there. So you use a straight edge to do your best to draw a dashed line. It's not quite a dashed line, I do apologize. It's a little harder on a screen, but I'll do my best. Didn't mention I'm left-handed too, so it's a little harder for either way. So I do kind of have a ghost of my asymptotes right here, but that is nice because it gives you an idea where the center is already located. It's where the diagonals are crossing. So I can see right away where my center is. So you could kind of note to yourself who the center is and just kind of be careful. It's always the x value that comes first. So we do have -2, but notice you do not have to move up or down for the y value, so we do have a 0. So if we are playing around with determining the equation, we're going to notice that the y value will not have a subtraction or addition to that y term. So you could kind of do a little bit of erasing there. I mean, well, I'll help you a little bit. Technically, you do have a y minus 0, but in a minute, you'll notice that, oh yeah, y minus 0 really shows us that we don't have any sort of shift in the vertical direction. But we do have the x term. In this case, it's the opposite of what we see, so we should have x plus 2 squared. So that's giving us our center. Be careful with the switch here. I know with ellipses, it was always the x term comes first, the y term comes second, but hyperbolas, you just always want to make sure the x values are consistent. So x value of the center goes with the x term, y value of the center goes with the y term. So now that you kind of have your vertices and the way the box is drawn, we can count to figure out who our A and our B are. So notice with the A, it has to do with the vertices. I can count. I'll kind of highlight this if I can in pink. I just want to figure out the length of that segment. It happens to be 3. So that's telling me that A is equal to 3, which gives me the fact that A squared will be 9. So now we can replace this with a 9. And now how far your box goes, you'd have to know this in order to figure out your B term. It's really hard to determine if you don't have a box with your hyperbola, unless you know a little more information. So with the B, I'm going to count outwards from the center, and I can highlight this in teal for you. You'll kind of see that there are 2 units from the center to the edge of that box in both directions. So that's telling me B is 2, which means B squared should be 4. So I can now replace this. And I've got my center, I've got my A and B, and that's all we needed for this equation of the vertical hyperbola. So you could kind of tell it takes a little counting. Let's move on to see what we can do. Center box is drawn for us. I will also, this might be a little harder for me to determine where my center is, but I do know I could kind of tell where my vertices are, but I'll draw my asymptotes first, just in case. Sometimes that helps me see a little better. Bonus if the asymptotes are already drawn in for you. I'm using my straight edge the best of my abilities. Notice that the asymptotes make the difference about how wide you make your parabola branches. And so it does appear that the intersection of those asymptotes are right here. So I could look at my center. I could label that right away. So if I count from my origin, careful, this is orientated a little differently. The origin is down here. My center is -1. And I have to count upwards, 1, 2, 3, 4. The scale's a little different, not little squares. They look more like rectangles. Now, again, just kind of emphasizing the way this parabola runs, you'll notice that it opens up to the left and opens up to the right. I said parabola, I meant hyperbola, sorry. Get mixed up with all those conic sections. But we do have the case of when you're opening left and opening right with the branches, you do have the case of a horizontal hyperbola. And it's important to recognize this because that determines what your equation looks like. So remember with the horizontal hyperbola, the x squared term comes first. There's a minus sign. Then the y squared term, still equal to 1. Just a reminder, hyperbola equations, they do have minus signs in some cases, separating the 2 squared terms. And it matters who the positive term is. So in this case, the positive term is the x minus h squared. So that's why we're kind of emphasizing the fact that we have a horizontal hyperbola. And then the a squared is associated with the positive term. So you can kind of see we already labeled who our center is. So what I could do is replace the h and the k. In this case, the opposite of what we see, so that we should have x plus 1 squared and y minus 4 squared. And now it's a matter of naming who our a is and who our b is. So remember with the a, if you count outwards, in this case, it'd be counting outwards left and right. You'll see that we want that distance so we can figure out who A is. So that would be, I have to do a little counting, 1, 2, 3, 4, 5, 6, 7, 8. So A would be 8, which will give me A squared being 8 times 8, which is 64. So right away I can replace that. And because we know how tall the box is, we get the B term, or the B square, by the distance from the center to the top of the box, or the bottom of the box, depending on how you go. So we can kind of count what that distance is, 1, 2, 3, 4, and 5. And in both directions, it is the same. So we have 5 here, and we have, where was it? The 8 over here. And so we should have b equals 5. So b squared equals 5 times 5, which is 25. And now we have the equation of this horizontal hyperbola. So this should set you up for this problem. I do want to point out one more thing to you. Eventually, they're going to ask us for equations of the asymptotes. And it's not necessarily something you necessarily have to memorize. You could look at the formulas, of course. But I would like to say A and B have a lot to do with the slope of the asymptotes. So if you don't mind, I'll kind of just give you an idea here. The slope of the asymptotes, it's either going to be a positive or negative slope because there's 2 of them. But you could actually do this from viewing the picture as opposed to memorizing. Is it A on top or is it B on top? Just kind of look at the definition of what slope means, which is rise over run. So if you kind of are just looking at one point on the graph, I'll look at this part B. And you're looking maybe from the center to the, oops, let me kind of highlight that in yellow. So if you just kind of count what's the difference, the center to the corner of the box, all you have to do is use your A and B and understand who's the rise. So the rise, in our case, is up 3, and the run is to the right 2. Or you can go down 3, if you go the other way, down 3 and left 2. So you already have the slope, and that's kind of nice. There's no need to have to memorize B over A over B. Same story here. Again, if we were looking at part C, not that it's asking for this, I'm just trying to help you for the future. If you pick one corner of the box and you talk about the rise over run from the center to that corner, you can see that the slope, well, plus or minus, because positive or negative, the rise in this case is 5 and the run is 8. And you could kind of tell by just viewing what the labels are looking like. And if you do look at the formal formulas, that's how they let you know that it's B over A versus A over B. But I like pictures to help me visualize this as opposed to memorizing all these extra facts. But feel free to verify both. And we'll discuss that a little bit more in the next examples. We'll see you then.